So here's something I want you to just sit with for a moment. Right now, wherever you are, you're lying still. Maybe your eyes are closed. Maybe the room is dark, and everything feels very contained. Your bed, your room, the walls around you. It all feels like it has edges, and that's how we experience most of life, right? Things have boundaries. The table ends. The road ends. The ocean meets the shore. We're edge-detecting creatures, really. Our brains are wired to find where one thing stops and another thing begins. So it's only natural that at some point, maybe when you were a kid staring up at the sky, maybe just last week in some idle moment, you asked the most human question imaginable. Where does it all end? Where's the edge? And if there is an edge, what's on the other side? That question, as simple as it sounds, is one of the deepest things a human being can ask. And the answer, or really the collection of answers, because it's not just one, is stranger and more beautiful than almost anything else in science. Tonight, we're going to walk through it. Slowly. No rush. We're going to talk about the edge of the universe, what it means, why it's confusing, and why even the smartest people who've ever lived have struggled with it. And we're going to start where all good stories start, which is way, way back, with people who looked up and tried to make sense of what they saw. Let's go back about 2,400 years to ancient Greece, because that's where some of the earliest serious thinking about this happened. And I want to tell you about a particular thought experiment, one that's so elegant it still holds up today. It comes from a philosopher named Archytas of Tarentum. He was a friend of Plato's, a mathematician, a statesman, and apparently a pretty brilliant guy all around. And Archytas posed this challenge. Imagine you could travel to the very edge of the universe, the absolute boundary of everything that exists. You get there, and you're standing at this wall, this limit. Now, he said, stretch out your hand, or throw a spear. What happens? If the spear passes through, then clearly there's more space on the other side, which means you weren't at the edge after all. But if the spear bounces back, if something stops it, well, what is that something? It's a thing. It's out there, which means there's something beyond where you thought the edge was. Either way, you can't win. Either way, there's more. And you can repeat this process forever. Walk to the new edge. Throw the spear again. Archytas concluded that the universe must be infinite, because any boundary you propose immediately implies something beyond it. Now think about what that means. 2,400 years ago, someone was already grappling with the logical paradox of cosmic edges. And honestly, we haven't fully escaped that paradox. We've refined it enormously. We've wrapped it in mathematics and observational data and general relativity. But the core tension Archytas identified, the weirdness of trying to put a boundary on everything, that's still with us. That's still the thing that makes this topic so wonderfully slippery. But here's the thing. The ancient Greeks didn't all agree with Archytas, not even close. Aristotle, who came along a generation or so later, and whose ideas would dominate Western thought for almost 2,000 years, had a very different picture. Aristotle's universe was finite. It had a definite structure. The earth sat at the center, motionless, and around it were these nested crystalline spheres. Imagine them like layers of an onion, each one carrying a celestial body. The moon on one sphere, the sun on another, the planets each on their own, and then way out at the outermost layer, the sphere of the fixed stars. And beyond that outermost sphere, nothing, not empty space, not darkness, literally nothing. Aristotle argued that nothing wasn't even a coherent concept in the way we might think of it. There was no space out there to be empty, no void waiting to be filled. The universe simply was what it was, and it ended at the stars. This is actually a more subtle idea than it first sounds. Aristotle wasn't saying there was a wall with empty space on the other side. He was saying that space itself didn't exist beyond the outermost sphere. There was no other side. And if that sounds a little bit like something a modern cosmologist might say, well, hold that thought, because we'll come back to it. For a long time, Aristotle's finite, neatly ordered cosmos was the dominant model. It was adopted and adapted by Islamic scholars, by medieval European thinkers, and most significantly, by the Catholic Church, which wove it into theology. The outermost sphere of the stars became associated with the heavens, with the dwelling place of God. The cosmos had a clear hierarchy. Earth at the corrupt, changeable center, the divine and perfect realm at the outer edge. It was tidy. It was reassuring. And it was, in a very real sense, a universe with an edge that people were comfortable with, because the edge was where God lived. But then, things started to crack. And this is where it gets really interesting. In 1543, Nicolaus Copernicus published his book, and you probably know the broad strokes. He proposed that the Earth wasn't at the center of everything, that instead, the Earth and the other planets orbited the Sun. Now, Copernicus himself was actually pretty conservative in some ways. He still believed in a finite universe. He still kept the sphere of the fixed stars as an outer boundary. He just moved the Sun to the center and pushed the Earth out to the cheap seats. But even that modest rearrangement had enormous implications for the edge question, because once you dislodge the Earth from the center, once you say we're not special, we're just another planet going around a star, you've opened a door that's very hard to close. And the person who kicked that door wide open was Giordano Bruno. Now, Bruno is a fascinating and tragic figure, and I want to spend a little time with him because his story matters. He was born in 1548 near Naples, became a Dominican friar, and almost immediately started getting into trouble for his ideas. He was brilliant, combative, and absolutely fearless in his thinking. And Bruno took the Copernican model and ran with it far beyond where Copernicus himself would have been comfortable. Bruno said, "Look, if the sun is just a star, and the stars are just other suns, then why should there be a boundary at all? Why should the universe have an edge?" He proposed that the universe was infinite, that it contained an infinite number of worlds, many of them inhabited, and that there was no center and no edge. The stars went on forever. This was radical. This was dangerous, and Bruno paid for it with his life. In 1600, after years of imprisonment and a trial by the Roman Inquisition, he was burned at the stake in the Campo de' Fiori in Rome. His cosmological ideas weren't the only charges against him. There were theological heresies of various kinds. But his vision of an infinite universe with no special place for Earth and no clear boundary for God's domain was deeply threatening to the established order. It's worth pausing on that. A man was killed, in part, because he suggested the universe might not have an edge. That's how deeply this question cuts. It's not just physics. It's about our place in things. It's about whether the cosmos is built around us or whether we're just somewhere in it, adrift in something that has no center and no boundary. Now, Bruno wasn't doing rigorous science in the way we'd recognize it today. He was working from intuition, from philosophy, from a kind of mystical conviction. But his intuition turned out to be remarkably close to where modern cosmology would eventually land. And the person who started putting real observational muscle behind these ideas was, of course, Galileo. Galileo didn't directly address the edge question in the way Bruno did, but what he did was arguably more important. He gave us the tool that would eventually blow the question wide open. When Galileo pointed his telescope at the night sky in 1609 and 1610, he saw things that no human had ever seen. He saw moons orbiting Jupiter, which meant not everything orbited the Earth. He saw the phases of Venus, which made much more sense in a sun-centered model. And he saw that the Milky Way, that hazy band of light across the sky, was actually made up of countless individual stars, far more than anyone had imagined. The universe was suddenly much, much bigger than it had seemed. And here's what's quietly revolutionary about that last observation. If the Milky Way is made of stars, and there are vastly more of them than we thought, then the sphere of the fixed stars starts to look less like a boundary and more like a neighborhood. It stops being an edge and starts being a place with depth and structure. The stars aren't all pasted on a single shell at the same distance. They're scattered through space at different distances. And once you realize that, the idea of a hard outer boundary becomes much harder to maintain. But the real conceptual leap, the one that would reshape everything, was still a couple of centuries away. And it would come from an unlikely source, not a philosopher, not an astronomer, but a clerk in a Swiss patent office who was thinking very carefully about what happens when you move very, very fast. We'll get to Einstein soon, but before we do, I want to linger on something that happened in the centuries between Galileo and Einstein, because there's a puzzle that emerged during that time that's directly relevant to the edge question. And it's one of those things that seems simple at first but turns out to be incredibly deep. It's called Olber's paradox, and it goes like this. If the universe is infinite, and if it's filled with an infinite number of stars scattered more or less evenly through space, then every line of sight, every direction you look, should eventually end on the surface of a star. Think about that. Imagine you're standing in a forest that goes on forever in every direction. If you look along any line of sight, eventually your gaze will hit a tree trunk. There's no gap, no direction where you can see to infinity without something blocking your view. In the same way, in an infinite universe full of stars, the entire night sky should be blazing with light. Every point in the sky should be as bright as the surface of a star. The night sky should not be dark. But it is dark. You can go outside right now and see it. The sky between the stars is black. So something about the simple picture, infinite universe, infinite stars, evenly distributed, must be wrong. And this paradox, which was discussed by various people over the centuries, but is named after the German astronomer Heinrich Wilhelm Olbers, who wrote about it in 1823. This paradox is quietly one of the most important clues about the nature of the universe's edge, or its lack of one. There are several possible resolutions. Maybe the universe isn't infinite. Maybe the stars haven't been shining forever. Maybe something is blocking the light. And the real answer, as it turns out, involves a combination of factors that we're going to unpack as we go deeper into this story. But the key insight is this. The darkness of the night sky is telling you something profound about the structure of the cosmos. It's a message written in the absence of light, and it took centuries for anyone to fully read it. And the person who gave us the framework to finally start reading it was a young physicist named Albert Einstein, who in 1915 published his general theory of relativity and, almost without meaning to, transformed the edge question from philosophy into physics. And that transformation changed everything. See, before Einstein, when people talked about whether the universe had an edge, they were essentially having a philosophical argument. You could reason about it. You could think up clever thought experiments like the spear toss, but you couldn't actually calculate anything. You couldn't write down an equation that described the shape of the universe and then solve it. But general relativity changed that, because what Einstein showed, and this is one of those ideas that sounds simple but is actually staggering, is that space itself has a shape. Space isn't just an empty stage where things happen. It's a thing. It bends, it curves, it stretches, it responds to the matter and energy inside it. Mass tells space how to curve, and curved space tells mass how to move. That's the famous summary, and it's remarkably accurate. Now think about what that means for our edge question. If space has a shape, then asking whether the universe has an edge is no longer a philosophical puzzle. It's a geometry problem, and geometry is something you can do math about. You can write down equations, plug in values, and get answers. Maybe not easy answers, but real ones, testable ones. Here's the analogy that helps the most. Think about the surface of the Earth. If you're an ant crawling on a basketball, your whole world is that two-dimensional surface. You can go north, south, east, west. But you never encounter an edge. You never walk up to a cliff where the surface just stops. And yet the surface isn't infinite either. It has a finite area. It wraps around on itself. If you walk in a straight line long enough, you come back to where you started. The surface of a sphere is finite but unbounded. It has no edge, but it doesn't go on forever. And this is the key idea that Einstein's framework made possible for the actual universe. Maybe the universe is like that. Maybe three-dimensional space curves back on itself, the way the two-dimensional surface of a sphere curves back on itself. Finite, but without a boundary. No edge, but not infinite. Einstein himself actually proposed exactly this in 1917, just 2 years after publishing General Relativity. He tried to apply his new equations to the entire universe, the whole thing, all of it, and he came up with a model. In Einstein's model, the universe was static, meaning it wasn't expanding or contracting. It was just sitting there, and it was shaped like the three-dimensional equivalent of a sphere. Mathematicians call this a three-sphere, or sometimes a hypersphere, and it's genuinely difficult to visualize because we're three-dimensional creatures trying to imagine a shape that curves through a fourth spatial dimension. But the concept is the same as the ant on the basketball. You could travel in any direction in a perfectly straight line, and if you went far enough, you'd come back to where you started. The universe, in Einstein's original model, had no edge, but it also wasn't infinite. It had a definite finite volume. And here's the thing. Einstein had to fudge his own equations to make this work. His equations naturally predicted that the universe should be either expanding or contracting. A static universe, one that just sits there unchanging, is unstable in general relativity. It's like trying to balance a pencil on its tip. Technically possible for an instant, but the slightest nudge sends it one way or the other. So Einstein added a term to his equations, a little mathematical constant that acted like a repulsive force, pushing space apart just enough to counterbalance gravity's tendency to pull everything together. He called it the cosmological constant, lambda, just a Greek letter and a number tucked into the equations to keep the universe still. He would later call this the biggest blunder of his career. But we'll come back to that, because the story of the cosmological constant has one of the most remarkable twists in all of science. For now, just hold on to this. Einstein, in 1917, had a model of the universe that was finite, had no edge, and wasn't expanding. And he needed a fudge factor to make it work. Now, while Einstein was wrestling with his equations in Berlin, other people were looking at the same math and coming to very different conclusions. And this is where a figure enters the story who doesn't get nearly enough credit. His name was Alexander Friedmann, and he was a Russian mathematician and meteorologist. Yes, meteorologist, a weather guy, working in Petrograd, which is what St. Petersburg was called at the time. Friedmann had survived World War I as a bomber pilot, flying observation missions over the Austrian front, and then survived the Russian Revolution, and then survived a typhus epidemic. By the early 1920s, he was teaching at the university in Petrograd and happened to get interested in Einstein's equations. And in 1922, Friedmann did something beautifully simple. He took Einstein's field equations and said, what if we don't add the cosmological constant? What if we just let the equations do what they naturally want to do? And what he found was that the equations predicted a universe that changes over time, a universe that either expands or contracts. The math was clean, it was elegant, and it was unsettling. Because it meant the universe had a history. It wasn't eternal and unchanging. It had a past that was different from its present, and a future that would be different still. Friedmann actually found multiple possible solutions. In one, the universe expands forever. In another, it expands for a while, slows down, stops, and then collapses back on itself. A big crunch. In yet another, it expands, but gradually decelerates, approaching a standstill, but never quite reaching it. And which scenario actually plays out depends on how much stuff is in the universe, how much matter and energy there is to generate gravitational pull. Think about that for a second. The fate of the entire cosmos, whether it expands forever or eventually collapses, comes down to a question of density. How much stuff is there per cubic meter of space on average? It's almost absurdly simple as a concept, and yet it determines everything. Friedmann published his results, and Einstein initially dismissed them. Einstein actually wrote a short note claiming Friedmann had made a mathematical error. Friedmann wrote back, politely, showing his work was correct. Einstein eventually acknowledged that the math was right, but he still didn't believe the universe was actually expanding. He thought Friedmann's solutions were mathematically valid, but physically meaningless. Just because the equations allow it doesn't mean nature does it. And then Friedmann died. In 1925, at the age of 37, from typhoid fever. Some accounts say he caught it after a balloon ascent where he was doing atmospheric research, though the exact circumstances are debated. He never lived to see his expanding universe solutions confirmed. He never knew he was right. But here's what's wild. Almost simultaneously, and apparently independently, a Belgian physicist and Catholic priest named Georges Lemaitre was working on the same problem. Lemaitre had studied at Cambridge, at Harvard, and at MIT. He was deeply trained in both physics and astronomy, and he was also a priest ordained in 1923, which gives his story this fascinating dual character. Here was a man of faith applying general relativity to the cosmos and arriving at conclusions that would reshape humanity's understanding of creation itself. In 1927, Lemaitre published a paper in a relatively obscure Belgian journal which is part of why it was initially overlooked, in which he independently derived the expanding universe solutions and went further than Friedman. Lemaitre connected the mathematics to actual astronomical observations. He looked at data showing that distant galaxies appeared to be moving away from us, and he proposed that this was because space itself was expanding. Not that galaxies were flying through space like shrapnel from an explosion, but that the fabric of space between galaxies was stretching, everything getting farther apart from everything else, like dots on the surface of a balloon being inflated. And this is a crucial distinction, one that matters enormously for the edge question. If galaxies were just flying apart through a pre-existing space, then you could ask, flying apart into what? What's out there at the edge, where the farthest galaxies haven't reached yet? But if space itself is expanding, if the expansion is space, then there's no edge to fly toward. There's no outside for things to expand into. The expansion is happening everywhere, at every point, simultaneously. It's not an explosion from a center. It's a stretching of the entire fabric. Let that settle for a moment, because it's one of those ideas that seems to make sense and then suddenly doesn't, and then makes sense again. There is no center of the expansion. Every point in the universe sees every other point moving away from it. If you were standing on a galaxy a billion light years from here, you'd look around and see all the other galaxies receding from you, and you'd think you were at the center. But so would someone on a galaxy a billion light years in the other direction. Everyone thinks they're at the center, and in a sense, everyone is, or no one is. It depends on how you want to frame it. Now, Lemaitre's paper didn't get much attention at first. Language barriers, an obscure journal, and the sheer strangeness of the idea all worked against it. But then, in 1929, the American astronomer Edwin Hubble, working at the Mount Wilson Observatory in the mountains above Los Angeles, using what was then the most powerful telescope in the world, the 100-inch Hooker telescope, published observations that would change cosmology forever. Hubble had been meticulously measuring the distances to galaxies and their redshifts. Redshift is what happens to light when its source is moving away from you. The light waves get stretched out, shifted toward the red end of the spectrum, the same way the pitch of an ambulance siren drops as it drives away from you. And what Hubble found was a clear pattern. The farther away a galaxy was, the faster it was moving away from us. This relationship was remarkably linear. Double the distance, double the recession speed. Triple the distance, triple the speed. This is Hubble's law, and it's exactly what you'd expect if space itself is expanding uniformly. It's not that distant galaxies are moving faster through space. It's that there's more space between us and them, and all of that space is stretching. More space means more total stretching, which means a higher apparent recession velocity. The observation fit Lemaitre's prediction perfectly. And here's where the story gets a little bittersweet, because Lemaitre had actually predicted this relationship 2 years before Hubble observed it. He'd even estimated a value for the expansion rate. But Hubble had the data, the prestigious observatory, and the American scientific establishment behind him. For decades, the expansion relationship was called Hubble's law, and Lemaitre's contribution was largely forgotten. It wasn't until 2018 that the International Astronomical Union officially renamed it the Hubble-Lemaitre Law, nearly a century late. But regardless of who gets the credit, the implication was seismic. If the universe is expanding now, then it was smaller in the past. Run the clock backward, and everything was closer together. Keep running it back, and everything was much closer together. Keep going, and you reach a point where all the matter and energy in the observable universe was compressed into an unimaginably dense, unimaginably hot state. Lemaitre called this the primeval atom. Today we call the event that started the expansion the Big Bang, a name that was actually coined as a joke by the astronomer Fred Hoyle, who didn't believe in it and was trying to make it sound ridiculous. The name stuck anyway. And this brings us to something that directly addresses our question about the edge of the universe, something that confuses almost everyone the first time they hear it, and honestly, the second and third time too. If the Big Bang happened, and the universe has been expanding ever since, then surely there must be an edge, a frontier, a boundary where the expansion hasn't reached yet. Surely the universe is expanding into something, right? And the answer, the deeply counterintuitive answer that general relativity gives us, is no. No, the universe is not expanding into anything. There is no empty room outside the universe waiting to be filled. There is no outside at all. The expansion of the universe is not like a balloon inflating inside a room. It's like the surface of the balloon itself stretching, except you have to throw away the room entirely. There is no room. There's only the surface. And I know that's maddening. I know that every instinct you have says, but there has to be something beyond it. There has to be a place where the universe stops and something else begins. And the reason that instinct is so strong is that you've spent your entire life navigating three-dimensional space, and your brain is extraordinarily good at thinking about objects inside containers. You put groceries in a bag. You put a bag in a car. You put a car in a garage. Everything is always inside something else. But the universe is not inside anything. It's not an object sitting in a larger space. It is space, all of it. And when we say it's expanding, we mean that the metric, the mathematical description of distances between points, is changing. The distances between things are getting larger, not because things are flying apart through some pre-existing void, but because the fabric of space itself is stretching. New distance is appearing between objects, and there's no edge to this process because there's no boundary where space gives way to not space. Let that sit for a moment. Just breathe with it. It's genuinely one of the strangest ideas in all of science, and nobody gets comfortable with it quickly. Einstein himself struggled with the implications of his own equations. So if it feels slippery, if it keeps almost making sense and then sliding away, that's completely normal. You're in excellent company. Here's an analogy that might help, and it's not perfect. No analogy for this is perfect, but it's the best one we've got. Think about an ant walking on the surface of a sphere. A very patient ant on a very large sphere. The ant can walk in any direction it wants. It can walk north, south, east, west. It can walk for its entire life, and it will never reach an edge. There is no edge to the surface of a sphere. The surface is finite. It has a definite, measurable area, but it's unbounded. There's no wall, no cliff, no boundary. The ant can't fall off. And if you ask the ant, "What's beyond the surface?" the question wouldn't quite make sense, because for the ant, the surface is all there is. The ant's entire universe is that two-dimensional surface. Beyond would require a third dimension that the ant doesn't have access to and can't perceive. Now, scale that up by one dimension. We're the ant. Our three-dimensional space might curve back on itself in a higher dimension that we can't perceive, creating something that's finite in volume but has no boundary, no edge, no wall. You could fly a spaceship in a straight line for billions of years, and never hit a wall. And in certain geometries, you might even end up back where you started, like the ant circumnavigating the sphere. That was essentially Einstein's 1917 model, the hypersphere. Finite, unbounded, no edge. But here's where it gets richer, because the universe doesn't have to be shaped like a hypersphere. General relativity allows for different geometries depending on how much stuff the universe contains, how much mass and energy are spread through it. And this brings us back to Alexander Friedmann's work, those solutions he found in 1922 that Einstein initially dismissed. Friedmann showed that the geometry of the universe falls into three basic categories, and each one depends on the density of matter and energy compared to a critical threshold. If the density is above the critical value, space curves in on itself, positive curvature, like the surface of a sphere. The universe is finite, closed, and eventually the expansion slows, stops, and reverses into a contraction. A big crunch. No edge, but a definite end in time. If the density is below the critical value, space curves the other way, negative curvature, like a saddle or a Pringle chip. The universe is infinite, open, and expands forever, with the expansion never quite slowing to a stop. No edge, no end, just endless thinning out. And if the density is exactly at the critical value, right on the knife's edge, space is flat. Euclidean geometry works. Parallel lines stay parallel forever. The universe is infinite, and the expansion slows down but never quite reaches zero, approaching it asymptotically like a curve that gets closer and closer to a line but never touches it. Three options, three shapes. And in all three cases, this is the crucial part, there is no edge. Whether the universe is finite and closed, or infinite and open, or infinite and flat, general relativity gives you no edge. The concept just doesn't arise. It's not that the edge is really far away and we haven't found it yet. It's that the mathematics of curved spacetime doesn't produce edges in the way our intuition expects. So which one is it? Which shape is our actual universe? And this is where the story shifts from pure theory to one of the most extraordinary observational campaigns in the history of science. Because by the mid-20th century, cosmologists realized that you could actually measure this. You could determine the geometry of the universe by looking at it carefully enough. But first, something else happened. Something that transformed the Big Bang from a controversial hypothesis into established science, and it happened almost by accident. In 1964, two radio astronomers at Bell Labs in Holmdel, New Jersey, Arno Penzias and Robert Wilson, were working with a large horn antenna that had originally been built for satellite communication. They were trying to calibrate it for radio astronomy, and they kept picking up a persistent, low-level microwave noise that they couldn't get rid of. It was coming from every direction. It didn't change with the time of day or the season. It wasn't coming from New York City. It wasn't coming from the Milky Way. They even climbed inside the antenna and cleaned out pigeon droppings, thinking that might be the source. It wasn't the pigeons. What Penzias and Wilson had stumbled onto was the cosmic microwave background radiation, the CMB, the afterglow of the Big Bang itself. And this is worth slowing down for, because the CMB is one of the most important things in all of cosmology, and it's directly relevant to our question about the edge of the universe. Here's what's happening. In the very early universe, we're talking roughly 380,000 years after the Big Bang, which sounds like a long time, but is basically the first eye blink in cosmic history. The universe was so hot and dense that atoms couldn't form. Electrons were flying free, And photons, particles of light, couldn't travel more than a short distance before smacking into an electron and being scattered in a random direction. The universe was opaque. It was like being inside a fog so thick you couldn't see your hand in front of your face. Light was trapped. But as the universe expanded, it cooled, and at about 380,000 years, the temperature dropped enough to roughly 3,000 Kelvin, which is about the temperature of the surface of a cool red star, that electrons could finally be captured by atomic nuclei to form neutral atoms, mostly hydrogen, and suddenly, with the free electrons swept up into atoms, photons had nothing to scatter off of. The fog cleared, light was released. The universe became transparent for the first time. That light, the light released at the moment the fog cleared, has been traveling through space ever since, for 13.8 billion years. And because the universe has been expanding all that time, the wavelength of that light has been stretched enormously. What started as visible light, the warm orange glow of a 3,000-degree plasma, has been redshifted all the way down into the microwave part of the spectrum. It now corresponds to a temperature of about 2.725 Kelvin, just a few degrees above absolute zero, and it fills the entire sky, coming from every direction, almost perfectly uniform. That's what Penzias and Wilson found. They were hearing the oldest light in the universe, the thermal echo of creation itself, stretched by expansion into a faint microwave hum. They won the Nobel Prize for it in 1978. And the discovery was a body blow to the steady-state theory championed by Fred Hoyle and others, which held that the universe had no beginning, that it had always existed in roughly the same state, with new matter continuously created to fill in the gaps left by expansion. The steady-state model had no natural explanation for a uniform background of microwave radiation. The Big Bang model predicted it. George Gamow and his colleagues Ralph Alpher and Robert Herman had actually predicted the existence and approximate temperature of this radiation back in the late 1940s, though their prediction had been somewhat forgotten by the time Penzias and Wilson made their discovery. Science is messy like that. The right answer sometimes sits in a journal for 15 years before anyone connects it to the right observation. But here's what makes the CMB truly extraordinary for our question about the edge of the universe. That wall of light, that moment when the fog cleared 380,000 years after the Big Bang, it's not just a relic. It's a boundary. Not a boundary in space, but a boundary in observability. We literally cannot see anything beyond it using light because before that moment, the universe was opaque. Light from earlier times was scattered and randomized. The CMB is like a curtain drawn across the past, and everything behind it is hidden. This gives us a concept that's absolutely central to the edge question, and it's one that most people conflate with the universe itself, but is actually something very different. It's called the observable universe. And the distinction between the observable universe and the entire universe is, I think, one of the most important ideas in all of cosmology, and one of the most commonly misunderstood. The observable universe is the region of space from which light has had time to reach us since the Big Bang. That's it. It's defined by the speed of light and the age of the universe. Light travels fast, about 300,000 kilometers per second, but it doesn't travel infinitely fast, and the universe has only existed for 13.8 billion years. So there's a maximum distance from which we can receive signals. Beyond that distance, light simply hasn't had enough time to make the trip. Now, you might think that means the observable universe has a radius of 13.8 billion light-years, and that's a completely reasonable guess. But it's wrong, and the reason it's wrong is expansion. Remember, While that light has been traveling toward us for 13.8 billion years, the space it's been traveling through has been stretching. The objects that emitted that light have been carried farther away by the expansion of space during the entire journey. So the actual current distance to the edge of the observable universe, the objects whose ancient light is just now reaching us, is about 46.5 billion light-years in every direction. That gives the observable universe a diameter of about 93 billion light-years. And here's the thing. The observable universe does have an edge. It's a sphere centered on you, right where you are right now, with a radius of 46.5 billion light-years. Beyond that sphere, there is almost certainly more universe, more galaxies, more stars, more space. We just can't see it yet, and some of it, depending on the rate of expansion, we may never see. Because space in the most distant regions is expanding faster than light can cross it, so the light from some objects will never, ever reach us, no matter how long we wait. So when someone asks, does the universe have an edge? The answer depends entirely on which universe you're talking about. The observable universe? Yes, absolutely, it has an edge, a horizon, defined by the finite speed of light and the finite age of the cosmos. But that edge isn't a wall or a boundary in space. It's a limitation on what we can observe. It's our horizon, not the universe's. If you were standing on a galaxy at the edge of our observable universe, you'd have your own observable universe centered on you, extending 46.5 billion light-years in every direction, overlapping with ours in some places and extending far beyond it in others. Every point in the universe has its own observable universe, like every person standing on a vast plain has their own horizon. But the universe itself, the whole thing, the totality of everything, does that have an edge? And this is where we have to confront something that's either thrilling or deeply unsettling, depending on your temperament. Because the honest answer is that we don't know for certain. General relativity tells us the shape of the universe depends on its density. And for decades, cosmologists were trying to measure that density, to figure out which of Friedman's three geometries we actually live in. And in the late 1990s, two separate things happened almost simultaneously that changed everything we thought we knew about the fate of the cosmos. The first was a heroic effort to measure the geometry of the universe directly, and the second was a discovery so shocking that the scientists who made it didn't believe their own data for months. Let's start with the geometry question, because that's where we left off. Remember Friedman's three options. The universe is either positively curved like a sphere, negatively curved like a saddle, or perfectly flat like an infinite tabletop. And the way you figure out which one you're in is by measuring the total density of everything in the universe. All the matter, all the energy, everything, and comparing it to a critical value. If the density is above critical, space curves back on itself, the universe is finite and closed. If it's below critical, space curves the other way, open and infinite. And if the density is exactly at the critical value, space is flat, perfectly, eerily flat. Now, measuring the density of the entire universe sounds like an absurd task, and in a way it is. But here's the clever thing. You don't actually have to weigh the universe. You can read the answer off the oldest light in existence. The cosmic microwave background, that relic glow from 380,000 years after the Big Bang that Penzias and Wilson stumbled into. Because that light has been traveling through the geometry of space for almost 13.8 billion years, and the geometry of space affects how that light looks when it arrives. Specifically, it affects the apparent size of the hot and cold spots in the CMB. Think of it this way. Imagine you're looking at a distant object and you know exactly how big it is, say a ruler that's exactly 1 meter long. If space is flat, the ruler looks a certain angular size from your vantage point. But if space is positively curved, like the surface of a sphere, the light rays bend in a way that makes the ruler look bigger than you'd expect. And if space is negatively curved, the ruler looks smaller. So, if you have a standard ruler in the early universe, something whose actual physical size you can calculate from first principles, you can measure its apparent angular size in the CMB and deduce the curvature of space. And here's the beautiful part. Such a standard ruler exists. In the early universe, before the CMB was released, the hot plasma of protons, electrons, and photons was sloshing around. Sound waves were rippling through it. Literal acoustic oscillations, compressions, and rarefactions moving through the primordial soup at roughly half the speed of light. And these sound waves had been traveling since the Big Bang, so by the time the universe cooled enough for the CMB to be released, the waves had traveled a specific, calculable distance. That distance, the sound horizon it's called, is your standard ruler. You know how big it should be. You can see its imprint in the CMB as the characteristic size of the hot and cold spots. So you measure the angular size of those spots, compare it to what you'd expect in flat, open, or closed geometries, and you have your answer. This is exactly what a series of experiments set out to do in the late 1990s and early 2000s. There were balloon-borne experiments like Boomerang and Maxima, launched from Antarctica, floating at the edge of the atmosphere, to get above the worst of the atmospheric interference. And then, in 2001, NASA launched WMAP, the Wilkinson Microwave Anisotropy Probe, which mapped the CMB from space with extraordinary precision. And later, in 2009, the European Space Agency launched Planck, which did it even better. And the answer came back, and it was remarkable. The universe is flat, or so close to flat that we cannot measure any curvature at all. The total density of the universe is within about 0.5% of the critical density. Space, as far as we can tell, is not curved in either direction. It's flat. Euclidean geometry, the stuff you learned in school, parallel lines never meeting, angles of a triangle adding up to 180 degrees, that appears to hold on the largest scales we can measure. Now think about what that means for the edge question. A positively curved universe would be finite but unbounded. You could walk forever and eventually come back to where you started, like circumnavigating the Earth. That's a universe with no edge but a definite, finite volume. A flat universe, on the other hand, in its simplest interpretation, is infinite. It just goes on forever in every direction. No edge, no boundary, no wrapping around. Just more space, more galaxies, more everything, forever. I want you to sit with that for a moment, because it's genuinely one of the most staggering things science has ever suggested. The universe might be literally infinite, not just really big, not just bigger than we can see, actually infinite. An infinite number of galaxies, an infinite number of stars, an infinite amount of space. And if that's true, then the observable universe, our little bubble, 93 billion light-years across, is an infinitesimally small patch of something that has no size at all, because infinity doesn't have a size. But here's where I need to be careful, because flat doesn't necessarily mean infinite. It's the simplest interpretation, but there are other possibilities. You could have a flat universe that's still finite if it has a weird topology, if it wraps around on itself in some way that's consistent with flat geometry. Think of a video game screen where you go off the right edge and appear on the left. That surface is flat. It obeys Euclidean geometry locally, but it's finite because it wraps. Mathematically, that's called a torus, and a flat universe with toroidal topology would be finite, no edges, and geometrically flat. Cosmologists have actually looked for evidence of this kind of wrapping in the CMB. You'd expect to see repeating patterns if the universe were smaller than the observable universe and wrapping around. And so far they haven't found any, which means either the universe is truly infinite, or if it does wrap, it wraps on a scale much larger than what we can observe. So the geometry question, the one Friedman posed back in 1922, has been answered as well as we can currently answer it. The universe appears flat, and it's either infinite or so large that its finitude is hidden beyond our horizon. Either way, no edge. But that was only the first of the two things that happened in the late 1990s. The second one is wilder, and honestly, it's one of the great plot twists in the history of science. Because while the CMB experiments were pinning down the geometry, two teams of astronomers were independently trying to measure something different. They were trying to figure out how fast the expansion of the universe is slowing down. See, ever since Hubble confirmed that the universe is expanding, the natural question was, what's the future of that expansion? Gravity pulls everything together, so you'd expect the expansion to be decelerating. The galaxies are flying apart, but gravity is tugging on them, slowing them down, like a ball thrown upward that gradually loses speed. The question was simply how fast the deceleration was. Is gravity strong enough to eventually stop the expansion and pull everything back into a big crunch? Or is the expansion fast enough that gravity will never quite catch up, and the universe will expand forever, just more and more slowly? To measure this deceleration, you need to look at very distant objects and figure out how fast the universe was expanding at different times in the past. And the tool for this is a particular type of exploding star called a Type 1a supernova. These are extraordinary events. They occur in binary star systems where a white dwarf, the dense remnant of a dead star, is stealing matter from a companion star. As the white dwarf gains mass, it approaches a critical threshold called the Chandrasekhar limit, about 1.4 times the mass of our Sun. And when it hits that limit, it can no longer support itself against gravitational collapse, and it detonates. The whole star, consumed in a thermonuclear explosion so bright it can outshine an entire galaxy for a few weeks. Here's what makes Type 1a supernovae so useful. Because they all explode at roughly the same mass. They all have roughly the same intrinsic brightness. They're standard candles. If you know how bright something truly is, and you measure how bright it appears, you can calculate how far away it is. And if you also measure the redshift of the host galaxy, you know how much the universe has expanded since that light was emitted. Plot distance against redshift for a whole collection of supernovae at different distances, and you can trace out the expansion history of the universe. You can see whether the expansion has been slowing down, and by how much. Two teams were racing to do this. One was the Supernova Cosmology project, led by Saul Perlmutter at Lawrence Berkeley National Laboratory, which had been working on this since the late 1980s. The other was the High Z Supernova Search Team, led by Brian Schmidt in Australia, with Adam Rees doing much of the data analysis at Berkeley. They were competitors, using slightly different methods, checking each other's work whether they wanted to or not. And in 1998, both teams announced their results. and the results were, to put it mildly, not what anyone expected. The distant supernovae were dimmer than they should have been, not by a lot, but consistently, unmistakably dimmer, which meant they were farther away than expected, which meant the universe hadn't just been expanding. It had been expanding faster and faster. The expansion wasn't decelerating at all. It was accelerating. This was so counterintuitive, so contrary to everything anyone had assumed, that both teams spent months trying to find errors in their data. They checked for dust that might be dimming the supernovae. They checked for evolution in the supernovae themselves. Maybe ancient supernovae were intrinsically different from nearby ones. They checked their calibrations, their software, their assumptions, and they couldn't make the result go away. The universe is accelerating. Think about what that means. Throw a ball into the air, and instead of slowing down, it speeds up. Something is pushing it. Something is counteracting gravity on the largest scales, and not just counteracting it, but overwhelming it. Something is driving the galaxies apart, faster and faster, with every passing moment. And here's where Einstein walks back onto the stage in the most ironic way imaginable. Remember his cosmological constant? The fudge factor he added to his equations in 1917 to keep the universe static, the one he later called his greatest blunder. After Hubble showed the universe was expanding, it turns out that term, or something very much like it, is exactly what you need to explain the accelerating expansion. The cosmological constant represents a kind of energy inherent to empty space itself, a constant energy density that doesn't dilute as space expands. As the universe gets bigger and matter spreads thinner, gravity weakens. But this energy of empty space stays the same everywhere, and eventually it wins. It becomes the dominant force driving the expansion, and the expansion accelerates. We call this dark energy, and that name is essentially an admission of ignorance. We don't know what it is. We can describe what it does. It acts like a repulsive force on cosmic scales, pushing space apart. But we don't understand its nature. It's not made of particles we've detected. It doesn't interact with light. It doesn't clump or cluster. It's just there, everywhere. And it accounts for roughly 68% of the total energy content of the universe, which means the majority of everything that exists is something we cannot see, cannot touch, cannot explain from first principles. And this brings us to a truly sobering inventory of the cosmos. When Planck and WMAP and the supernova teams and galaxy surveys all combined their data, the picture that emerged was this. The universe is about 68% dark energy, about 27% dark matter, another mysterious substance we've never directly detected, which we know exists because of its gravitational effects on galaxies, and only about 5% ordinary matter. The stuff you and I are made of, the atoms, the protons and neutrons and electrons, the stars and planets and gas clouds, all of that is a tiny sliver of what's actually out there. Everything we've ever seen through every telescope ever built, every particle we've ever detected in every accelerator, represents roughly 1/20th of the universe's contents. And here's why this matters for our edge question. The accelerating expansion driven by dark energy doesn't just determine the future of the universe, it determines what we can ever hope to see of it. Because if the expansion keeps accelerating, and everything we know suggests it will, then the observable universe isn't just limited in size, it's shrinking, in a sense. Galaxies that are currently near the edge of our observable universe are being carried away from us faster than light. And as the expansion accelerates, more and more galaxies will cross that threshold, their light red-shifted into oblivion, fading from view forever. In the far, far future, trillions of years from now, astronomers in our galaxy, if there are any, will look out into the sky and see nothing, or almost nothing. The Milky Way may be merged by then with Andromeda into some giant elliptical galaxy, would sit in what appears to be a completely empty universe, no other galaxies visible anywhere. The cosmic microwave background, that ancient glow we spent so much time talking about, would be stretched to wavelengths so impossibly long that no conceivable instrument could detect it. The evidence for the Big Bang itself would be erased. Think about what that means. A civilization arising trillions of years from now, brilliant and curious and building their own telescopes, would look out and reasonably conclude that their galaxy was the entirety of the cosmos, a single island of stars floating in an infinite static void. They would have no way of knowing that the universe was expanding, no way of knowing about the Big Bang, no way of knowing about the hundreds of billions of galaxies that once filled the sky. The evidence would simply be gone, carried beyond the cosmic horizon by the very expansion that defines our universe. This idea was explored beautifully by Lawrence Krauss and Robert Scherer in a paper they published around 2007. They called it a kind of cosmic dark age, not a dark age of ignorance, but a dark age imposed by physics itself. The universe would be hiding its own history, and the haunting part, the part that should keep you up at night if you weren't trying to fall asleep, is the question it raises about us, right now. How do we know we're not already in a version of that situation? How do we know there isn't evidence of something grander, something that existed before our observable window opened, that has already been carried beyond our horizon? We assume we're living in a cosmologically privileged time, a time when we can still see the afterglow of the Big Bang, still detect distant galaxies, still piece together the story. And maybe we are. But there's a certain humility in admitting that the universe doesn't owe us a complete picture. So let's sit with this for a moment, because it connects back to our central question in a way that's actually quite profound. We started this whole journey asking whether the universe has an edge, and by now, you can probably feel how the question has transformed. It's not that we found the edge or proved there isn't one. It's that the concept of an edge has been replaced by something more subtle: horizons. The observable universe has a horizon, a boundary beyond which light hasn't had time to reach us. Dark energy is creating another kind of horizon, an event horizon for the cosmos, beyond which light emitted right now will never reach us, no matter how long we wait. These aren't edges in the way Archytas imagined, walls you could walk up to and poke a spear through. They're limits on information, limits on what we can know. And here's the thing. This distinction between different kinds of horizons is worth unpacking, because people mix them up all the time, and the differences matter. The first kind, the particle horizon, is the one we've been calling the edge of the observable universe. It's defined by the age of the universe and the expansion history. Light has been traveling toward us for 13.8 billion years. And because space has been expanding the whole time, the stuff that emitted the oldest light we can see is now about 46.5 billion light years away. That's the particle horizon. Everything inside it is, in principle, observable. Everything outside it is not, yet. And that yet is important, because in a decelerating universe, the particle horizon grows over time, New light from more distant objects keeps arriving. Your observable universe gets bigger. But now layer on the second kind, the event horizon created by accelerating expansion. In an accelerating universe, there's a distance beyond which light emitted today will never reach us. Ever. Not in a billion years, not in a trillion. The expansion of space between here and there is too fast and getting faster, and that light is swimming against a current it can never overcome. So while the particle horizon tells you what you can see from the past, the event horizon tells you what you'll ever be able to see from the future. And in our universe, that event horizon is shrinking. The sphere of galaxies whose future light can reach us is getting smaller over time. We are, in a very real sense, losing the universe. Piece by piece, galaxy by galaxy, the cosmos is disappearing behind an informational curtain. Now, you might be thinking, okay, but does the actual universe end at any of these horizons? And the answer, as far as we can tell, is no. The universe almost certainly continues beyond every horizon we can define. The cosmic microwave background looks the same in every direction, which tells us that conditions beyond our horizon are probably much like conditions within it. Galaxies, clusters, voids, the same large-scale structure repeating, perhaps forever. The horizon isn't a wall, it's just the limit of our view. But this raises a genuinely weird possibility that physicists have taken surprisingly seriously, and it connects to the flatness result we talked about earlier. If the universe is spatially flat and infinite, truly infinite, then it contains an infinite amount of space and, presumably, an infinite amount of matter arranged according to the same physical laws. And if you have infinite space and finite physics, meaning a finite number of possible configurations of particles within any given volume, then somewhere out there, impossibly far away, every possible arrangement of matter must repeat, including, in principle, an exact copy of you, lying in bed, listening to this, thinking this exact thought. This isn't mysticism. It's a straightforward consequence of infinity combined with finite quantum states. The physicist Max Tegmark has written extensively about this, calling it the level 1 multiverse, not parallel dimensions or branching timelines, just the simple, almost boring implication that an infinite universe must contain duplicate patches. The nearest copy of our observable universe, if you run the numbers, would be absurdly far away. Something like 10 to the power of 10 to the power of 118 meters from here. That number is so large it's essentially meaningless. You could write zeros for the rest of your life and not get close to writing it out. But meaningless, in practical terms, doesn't mean wrong in physical terms. If the universe is truly infinite and truly uniform on the largest scales, the math says those copies exist. You'll never see them, never interact with them, never detect them in any way. They're beyond every horizon, present and future, but they're a logical consequence of the cosmology we've built from CMB measurements and supernova data and galaxy surveys. And this is where the edge question gets almost philosophical, because if the universe is infinite, it doesn't have an edge by definition. Infinity means there's always more. You can never reach a boundary because there isn't one. But if the universe is finite, say, a 3 torus, that donut-like topology we mentioned, then it also doesn't have an edge because it wraps around on itself. You'd travel in a straight line and eventually come back to where you started, like circumnavigating the Earth, but in 3 dimensions. Either way, no edge. The universe has managed to eliminate the concept of an edge entirely, replacing it with either infinity or curvature, or both. But let's come back to something more concrete, because there's a piece of this story we haven't fully explored, and it's one of the most active areas of research in cosmology right now. We've talked about dark energy as if it's a settled thing, a cosmological constant, a fixed energy density permeating all of space, unchanging over time. And that's the simplest model, the one that fits the data best so far. It's called lambda CDM, where lambda is Einstein's cosmological constant and CDM stands for cold, dark matter. This model, with its 6 or so free parameters, fits an astonishing range of observations: the CMB, the expansion rate, the distribution of galaxies, the abundances of light elements from Big Bang nucleosynthesis. It's been called the standard model of cosmology, and for good reason. But here's what's really interesting. There are cracks. Small ones, maybe. Possibly just systematic errors or statistical flukes. But they're there, and they've been getting harder to ignore. The most famous is the Hubble tension. Remember Edwin Hubble measuring the expansion rate back in 1929? Well, that expansion rate, the Hubble constant as it's called, can be measured in 2 very different ways. You can measure it locally by looking at nearby supernovae and Cepheid variable stars and calculating how fast galaxies are moving away from us right now. Or you can infer it from the CMB by using the Planck satellite's exquisitely detailed map of the early universe and running the lambda CDM model forward to predict what the expansion rate should be today. And here's the problem. These 2 numbers don't agree. The local measurements, led by Adam Rees, the same Rees who co-discovered the accelerating expansion in 1998, consistently give a value around 73 kilometers per second per megaparsec. The CMB-based prediction from Planck gives about 67.4. That might not sound like a big difference, but both measurements have gotten so precise that the gap is now statistically significant, around 4 to 5 sigma, depending on whose analysis you trust. In physics, 5 sigma is traditionally the threshold for claiming a discovery. We're right at the edge of that. So what does this mean? If it's a real discrepancy and not some subtle measurement error, and a lot of very smart people have spent years trying to find the error without success, then it means our standard model of cosmology is incomplete. Something about lambda CDM is wrong, or at least missing a piece, and the candidates for that missing piece are fascinating. Maybe dark energy isn't constant. Maybe it changes over time, or varies from place to place. There's a whole class of models called quintessence, where dark energy is a dynamic field rather than a fixed constant. In some of these models, the expansion history of the universe is subtly different from what lambda CDM predicts, and that difference could show up as a mismatch in the Hubble constant, depending on how you measure it. Or maybe there's something about the early universe we don't understand. Extra relativistic particles, some new form of radiation, an unexpected phase transition. Maybe dark matter interacts with ordinary matter in ways we haven't accounted for. The point is, the Hubble tension is exactly the kind of crack that, in the history of physics, has sometimes blown open into a revolution. It might be nothing. Or it might be the first hint of something genuinely new about the universe. And there are other tensions too. The S8 tension, for instance, which involves how clumpy matter is on large scales. Some measurements suggest the universe is slightly smoother than lambda CDM predicts. Again, small discrepancies. Again, possibly systematic errors. But they're accumulating, and they all point in the same direction. Our picture of the universe, as spectacularly successful as it is, might still be missing something fundamental about the nature of dark energy, or dark matter, or both. This matters for our edge question, because the nature of dark energy determines the ultimate fate of the universe, and, with it, the nature of whatever boundary or boundlessness the cosmos possesses. If dark energy is truly constant, the universe expands forever, accelerating, and the story ends with that lonely galaxy in an empty sky. But if dark energy can change, if it can grow stronger over time, then you get scenarios that are far more dramatic. There's one called the Big Rip, proposed by Robert Caldwell and colleagues around 2003, where dark energy's density increases without bound. In that scenario, the expansion eventually becomes so violent that it tears apart galaxy clusters, then galaxies, then solar systems, then planets, then atoms themselves. The fabric of space literally rips apart at every scale. The universe doesn't just expand forever, it destroys itself in a finite time. And in that case, the edge of the universe becomes something terrifyingly literal. A wavefront of destruction expanding outward from every point in space simultaneously. Or dark energy could weaken over time, or even reverse sign, turning from a repulsive force into an attractive one. In that case, you could get a big crunch. The expansion slows, stops, reverses, and the universe collapses back on itself, perhaps into another singularity, perhaps into another Big Bang. Some physicists have speculated about cyclic models, where the universe bounces between expansion and contraction eternally, each cycle erasing the evidence of the last. In those models, the edge isn't spatial at all, it's temporal. The universe has a beginning and an end in time, but in space it might stretch on without limit, or wrap around in some topology we can't detect. The boundary is a moment, not a place, a wall in time, not in distance. And that idea, that time itself could have edges even if space doesn't, is one of those thoughts that sneaks up on you slowly and then just sits there, refusing to leave. Let's stay with that for a moment, because cyclic models have a surprisingly long intellectual history. The idea that the universe might pulse, expanding, collapsing, expanding again, goes back at least to ancient Hindu cosmology, where the universe cycles through vast epochs called kalpas, each one lasting billions of years before dissolving and being reborn. But in modern physics, the idea got serious traction after Friedman's equations showed that a universe with enough matter would eventually recollapse. If you could somehow survive the crunch, or if the physics allowed for a bounce rather than a true singularity, then maybe the whole thing starts over. Richard Tolman explored this in the 1930s, working out what a cyclic universe would look like under general relativity, and he ran into a problem: entropy. Each cycle, the total entropy of the universe would increase. That's just the second law of thermodynamics doing its thing, and increasing entropy means each successive cycle would be longer and larger than the last. Run the clock backward, and the cycles get shorter and shorter, until you hit a beginning anyway. So Tolman's cyclic model didn't really escape the need for a first moment, it just pushed it back. But the idea refused to die. In 2001, Paul Steinhardt at Princeton and Neil Turok, then at Cambridge, proposed something called the ekpyrotic model, later developed into the cyclic model, which drew on ideas from string theory. In their picture, our universe is a three-dimensional membrane, a brain, they called it, floating in a higher dimensional space. And there's another brain nearby, separated from us in this extra dimension. Periodically, these two brains collide, and each collision is a big bang, a fresh start for the universe on each brain. The collision releases enormous energy, creating matter and radiation, and the brains bounce apart, expand, cool, form galaxies, and eventually the dark energy on each brane drives everything apart until the branes are drawn together again by a force acting in the extra dimension. Then they collide again. Another Big Bang. Another cycle. Now, here's what's clever about this. In the Steinhardt-Turok model, the entropy problem gets handled differently because the universe expands so enormously during each cycle that the entropy density, the entropy per unit volume, gets diluted to essentially nothing before the next collision. The total entropy goes up, sure, but the universe is so much bigger that it doesn't matter locally. Each new cycle starts with conditions that look like low entropy, like a fresh beginning, even though globally the entropy has been climbing all along. Whether this actually works in full mathematical detail is still debated, and the model has its critics, quite vocal ones actually. But the point for us is what it does to the concept of an edge. If the cyclic model is right, there's no ultimate beginning and no ultimate end. Time stretches infinitely in both directions. The Big Bang that started our observable universe was just the most recent collision in an eternal sequence. And space, in each cycle, might be infinite. So you'd have a universe with no edge in space and no edge in time, no boundary anywhere, in any direction, in any dimension, just cycles within infinity. But you know, most working cosmologists today don't work with cyclic models. The standard picture, lambda CDM, doesn't require them, and the observational evidence we have, the cosmic microwave background, the distribution of galaxies, the abundance of light elements, all fits beautifully with a single Big Bang followed by expansion. The cyclic model can be made to fit the same data, but it requires extra machinery, extra assumptions, and it makes very few predictions that differ from the standard picture. So it remains a fascinating possibility rather than a leading theory. It's one of those ideas that lives at the boundary between physics and philosophy, which, when you think about it, is exactly where our whole question about the edge of the universe has always lived. So let's come back to what we actually know, what the observations are telling us right now, and what the near future might reveal. Because there's been some genuinely exciting and genuinely unsettling news in the last few years that bears directly on whether the universe will expand forever, collapse, or do something nobody predicted. In 2024, results from the Dark Energy Spectroscopic Instrument, DESI, started coming in. DESI is a remarkable piece of engineering mounted on the 4-meter Mayall telescope at Kitt Peak in Arizona. It can measure the spectra of 5,000 galaxies simultaneously, mapping the three-dimensional distribution of galaxies across enormous volumes of space. And what it's doing is measuring something called baryon acoustic oscillations, BAO for short. These are subtle patterns in the distribution of galaxies that trace back to sound waves in the early universe, pressure waves that rippled through the hot plasma before the cosmic microwave background was released. Those waves left a characteristic imprint, a preferred distance scale between galaxies that acts like a cosmic ruler. By measuring how that ruler appears at different distances, and therefore different times in cosmic history, you can track how the expansion rate has changed over billions of years. It's a beautiful technique, and it's one of the most precise tools we have for studying dark energy. Here's the thing. DESI's early results, combined with supernova data and CMB measurements, hinted, carefully, tentatively, with appropriate caveats, that dark energy might not be constant, that the equation of state of dark energy, the parameter cosmologists call W, might be changing over time. In the standard lambda CDM model, W equals exactly -1, always has, always will. That's what a cosmological constant does. It's constant by definition. But DESI's data showed mild statistical preference for models, where W was more negative than -1 in the past and has been moving toward less negative values, meaning dark energy might be weakening over time. Now, let me be careful here, because this is exactly the kind of result that gets overhyped. The statistical significance was modest, interesting, worth following up, but not the kind of 5 sigma detection that makes physicists pop champagne. And there are systematic uncertainties in how you combine different data sets that can shift the results. But even as a hint, it's provocative, because if dark energy is weakening, the implications for the fate of the universe are profound. A weakening dark energy could mean the acceleration of expansion eventually slows. It could even mean the acceleration stops and the expansion begins to decelerate again. And if dark energy weakens enough, or reverses sign entirely, you're back in big crunch territory. The universe that we thought was destined for eternal cold isolation might instead be headed for a collapse. Some physicists, including Andrei Linde and others, have pointed out that certain string theory-inspired models of dark energy naturally produce this kind of behavior. A dark energy field that starts strong and gradually decays. In those models, what we call the cosmological constant isn't really constant at all. It's the current value of a field that's been slowly rolling down a potential energy landscape for billions of years. Quintessence, remember. That idea we touched on earlier. If DESI's hints hold up with more data, quintessence or something like it would become a serious contender to replace the cosmological constant in our standard model. And this matters enormously for the edge question, because a cosmological constant gives you a very specific future, eternal expansion, an event horizon that permanently hides most of the universe from view, and a slow fade to darkness. The edge of the observable universe becomes a permanent boundary, a horizon beyond which you can never see or reach or even send a signal to. But a dynamic, dark energy changes the game. If dark energy weakens, the event horizon could recede. Galaxies that were being carried away from us might slow their recession. In principle, the observable universe could grow, revealing regions that were previously beyond our horizon. We'd see more, not less, as time went on. The edge would retreat, or in the big crunch scenario, the edge becomes a closing wall. Everything we can see starts rushing toward us, or rather, we all rush toward each other, and the observable universe shrinks as space itself contracts. The edge moves inward. The universe gets smaller, and eventually, everything meets at a point. Think about what that means for a moment. We've been talking about the edge of the universe for this entire journey, from Archytas throwing his spear at the boundary of the heavens, to Einstein curving space into a hypersphere, to the cosmic microwave background painting a picture of a flat, possibly infinite cosmos. And after all of that, the answer to does the universe have an edge might depend on a measurement we haven't finished making yet. It might depend on the precise behavior of a mysterious energy field that makes up more than 2/3 of everything that exists, a field we discovered only 26 years ago, a field whose fundamental nature remains completely unknown. That's humbling, and it's exciting, because it means cosmology isn't finished. The story isn't over. There are space missions being planned right now. The European Space Agency's Euclid satellite launched in 2023. NASA's Nancy Grace Roman Space Telescope is expected to launch in the mid-2020s. That will map the distribution of galaxies with unprecedented precision, measuring how dark energy has behaved across cosmic time. DESI will continue collecting data for years. The Vera C. Rubin Observatory in Chile, with its enormous wide-field camera, will survey billions of galaxies, tracking how the large-scale structure of the universe has evolved. Each of these instruments is, in its own way, trying to answer the same question that Archytas asked 2,400 years ago. What happens at the boundary? And here's something worth sitting with as you lie there in the dark. The tools we're using to probe the edge of the universe are themselves products of the same physics that governs the universe's structure. The silicon detectors in DESI's focal plane work because of quantum mechanics. The mirrors in the Roman telescope are shaped to nanometer precision, using the same understanding of optics that let Galileo see Jupiter's moons. The computers that process the data run on chips whose transistors are so small that quantum tunneling is a design constraint. We are using the universe's own laws, encoded in instruments built from the universe's own matter, to ask the universe about its own boundaries. There's a circularity there that's almost poetic. But there's also a deeper question lurking beneath all of this, one that physicists and philosophers have been circling around for decades, and it connects to something we haven't really addressed yet: the question of what lies beyond the observable universe, and whether beyond even means anything. Because when we talk about the edge of the observable universe, we're talking about a horizon, a limit on what we can see, not a limit on what exists. The universe almost certainly continues beyond that horizon, with more galaxies, more stars, more space. But how far? And is the stuff out there the same as the stuff in here? Or could the universe, at truly enormous scales, be fundamentally different from one place to another? That's the question, and it's one that takes us into some of the strangest territory in all of modern cosmology. Let's start with what we're fairly confident about. The observable universe, that sphere centered on us with a radius of about 46.5 billion light-years, contains something like 2 trillion galaxies. The cosmic microwave background, that ancient light from when the universe was only 380,000 years old, looks almost exactly the same in every direction. The temperature varies by only about 1 part in 100,000. That uniformity tells us something important. It tells us that the early universe was extraordinarily smooth, extraordinarily homogeneous. And the simplest assumption, the one that cosmologists have leaned on for over a century, is that this homogeneity continues beyond our horizon, that the universe out there looks pretty much like the universe in here. More galaxies, more clusters, more voids, more of the same cosmic web stretching on and on. This assumption even has a name. It's called the cosmological principle, the idea that on sufficiently large scales, no place in the universe is special. There's no center, no edge where things suddenly change, no preferred location. Everywhere looks roughly like everywhere else. And here's the thing, the cosmological principle isn't just a philosophical preference. It's baked into the mathematics of general relativity as we apply it to cosmology. The Friedmann equations, those equations that Alexander Friedmann worked out back in 1922, the ones that describe how the universe expands, they assume homogeneity and isotropy from the start. The whole framework of lambda CDM, the standard model of cosmology that we've been building up throughout this conversation, rests on that assumption. And it works remarkably well. The predictions match the observations to extraordinary precision. So, there's good reason to take the cosmological principle seriously. But taking it seriously and knowing it's true are two very different things. Because here's what's wild. We can't actually test the cosmological principle beyond our observable universe. We can test it within our horizon, and it holds up beautifully. The distribution of galaxies, the cosmic microwave background, the abundance of light elements. Everything is consistent with a universe that's the same everywhere we can see. But beyond the horizon, we're extrapolating. We're assuming that the pattern continues. And that's a reasonable assumption, but it's an assumption nonetheless. Now, you might be thinking, okay, so the universe probably just keeps going with more of the same. What's the big deal? And honestly, that might be the answer. It might be galaxies all the way out, forever, in every direction. And the story ends there. An infinite, uniform cosmos with no edge, no boundary, no surprises. But several ideas in modern theoretical physics suggest that the story might be much stranger than that. And the strangest of these ideas comes from a process that may have happened in the very first fraction of a second after the Big Bang, a process called inflation. We touched on the Big Bang earlier, but we didn't really dig into what happened in those earliest moments. And this is where it gets genuinely mind-bending. In 1980, a young physicist at Stanford named Alan Guth was working on a completely different problem. He was trying to understand why the universe doesn't seem to contain magnetic monopoles, these hypothetical particles that grand unified theories predicted should be everywhere, but that nobody had ever found. And in the process of thinking about that puzzle, Guth stumbled onto an idea that would transform cosmology. He proposed that in the first tiny sliver of a second after the Big Bang, we're talking about something like 10 to the minus 36 seconds, an almost inconceivably brief moment, the universe underwent a period of exponential expansion. Not the steady, gradual expansion that Hubble observed, but a violent, runaway doubling and redoubling of space itself. In a fraction of a second, a region smaller than a proton inflated to something vastly larger than the entire observable universe today. This sounds absurd, and when Guth first proposed it, plenty of physicists were skeptical. But inflation solved so many problems at once that it quickly became the leading framework for understanding the early universe. It explained why the cosmic microwave background is so uniform. Regions that look like they could never have been in contact with each other actually were in contact before inflation stretched them apart. It explained why the universe is spatially flat, or very nearly so. Inflation drives the geometry toward flatness the way inflating a balloon makes its surface look flatter and flatter. It explained the absence of magnetic monopoles. They were diluted to essentially zero density by the enormous expansion, and it even provided a mechanism for the tiny temperature fluctuations in the CMB. Quantum fluctuations in the inflating field, stretched to cosmic scales, became the seeds of all the structure we see today. Galaxies, clusters, the entire cosmic web, all of it traceable back to quantum jitters during inflation. But here's where inflation connects to our question about the edge of the universe, and it's a connection that keeps theoretical physicists up at night. In the early 1980s, shortly after Guth's original proposal, physicists, including Andrei Linde in the Soviet Union and, independently, Paul Steinhardt and Andreas Albrecht in the United States, developed improved versions of inflation that avoided some technical problems with Guth's original model. And as they explored the mathematics, they discovered something unsettling. In many versions of inflation, the process doesn't stop everywhere at once. Instead, inflation ends in some regions, our region, for instance, while continuing in others. The regions where inflation stops become pocket universes, each one potentially vast, each one cooling down, forming matter, developing its own cosmic history. But the space between them keeps inflating, stretching faster than light, pushing these pocket universes apart so rapidly that they can never come into contact with one another. This is what physicists call eternal inflation, and if it's correct, the implications are staggering. Our entire observable universe, all 46.5 billion light-years of it, would be just one pocket in an incomprehensibly vast, eternally inflating multiverse. And here's the part that connects directly to the edge question. In this picture, the universe doesn't have an edge in any traditional sense. It's not that there's a boundary somewhere far away. It's that the very concept of a single, coherent universe with a definable extent may not apply. There could be an infinite number of pocket universes, each one isolated from the others by eternally inflating space, each one potentially with different physical properties. And that last part, different physical properties, is what makes this truly strange. In some versions of string theory, the fundamental constants of nature, things like the strength of gravity, the mass of the electron, the cosmological constant, aren't fixed by the theory itself. Instead, they depend on the particular way that extra dimensions of space are compacted, and there are an enormous number of possible compactifications. Estimates suggest something like 10 to the 500th power different possibilities. If eternal inflation is real, and if string theory is on the right track, then different pocket universes might have different physical constants, different strengths of forces, different particle masses, different numbers of spatial dimensions even. Some of those universes might allow stars and galaxies and chemistry and life. Most of them probably wouldn't. This is the landscape multiverse, sometimes called the string theory landscape, and it was articulated most forcefully by Leonard Susskind at Stanford around 2003. And it's deeply controversial. Not because the mathematics is wrong, the math is consistent, but because it may be untestable. If other pocket universes are forever beyond our observable horizon, separated from us by eternally inflating space, then we can never see them, never detect them, never confirm or deny their existence. And that raises a profound question about what counts as science. Is a theory scientific if it makes no predictions that can be checked? Some physicists, like Susskind, argue that the multiverse is a natural consequence of our best theories and should be taken seriously even if direct observation is impossible. Others, like Paul Steinhardt, who, remember, helped develop inflation in the first place, have become deeply skeptical, arguing that a theory that can explain anything explains nothing. So let's sit with this for a moment. Think about what it means for the edge of the universe. If eternal inflation is correct, then asking, what's at the edge, is a bit like asking, what's north of the North Pole? The question assumes a structure that may not exist. There is no edge. There's no boundary you could reach where the universe stops. There's just more universe, and then more inflating space, and then more pocket universes, and then more inflating space, on and on, possibly forever. The edge isn't a place, it's an absence of the very framework that would make edge a meaningful concept. But you know what's fascinating? Even within this picture, our observable universe still has its horizons. The cosmic event horizon we talked about earlier, the one created by the accelerating expansion, that's still real, still meaningful, still defining what we can and cannot access. And if the DESI results hold up, if dark energy really is weakening over time, that event horizon might shift. It might recede, giving us access to more of our own pocket universe. We still wouldn't be able to see other pocket universes, Eternal inflation guarantees that, but we might learn more about the shape and extent of our own little patch. And this brings us to something that I think is genuinely beautiful about the whole enterprise. We started this journey with Archytas standing at what he imagined to be the edge of the cosmos, thrusting his hand outward, asking what would happen. And 2,400 years later, we're still asking essentially the same question, just with better tools and a much deeper understanding of how strange the answer might be. The edge has retreated from the sphere of fixed stars to the walls of the observable universe, to the boundaries of an inflationary pocket in an eternal multiverse. At every stage, what we thought was the edge turned out to be just another horizon, with more universe beyond it. But there's one more layer to this story, one more way of thinking about edges and boundaries that we haven't explored yet, and it connects to something that might be the deepest question of all. Not the spatial edge of the universe, but the edge of what we can ever know about it. Because there's a difference between what exists and what is in principle knowable, and modern physics suggests that the gap between those two things might be growing forever. And that's a remarkable thing to sit with for a moment. Not just that we don't know everything. That's obvious, that's always been true. But that the universe might be structured in a way that guarantees we can't know everything, no matter how clever we get, no matter how long we wait, no matter what instruments we build. The unknowability isn't a temporary limitation. It might be a feature of reality itself. Let me try to unpack that, because I think it's one of the most profound ideas to come out of modern cosmology, and it doesn't get talked about nearly enough. Start with something concrete. Right now, the observable universe has a radius of about 46.5 billion light-years. That's a lot of space. It contains something like 2 trillion galaxies, give or take. And within that volume, we can in principle observe everything. Every photon, every gravitational wave, every neutrino that's had enough time to reach us since the Big Bang. The key phrase there is in principle. In practice, we're limited by our instruments, by noise, by the faintness of distant signals. But there's no fundamental law preventing us from detecting any event that occurred within our observable universe. The information is out there, encoded in light and particles, waiting for us to catch it. But beyond that observable boundary, that's where things change. And they change not because of engineering limitations, but because of physics. The expansion of space, especially the accelerated expansion driven by dark energy, means that light from sufficiently distant regions will never reach us. Not in 1 billion years, not in 1 trillion, not ever. Those regions are receding from us faster than light can cross the gap. And before you object, no, this doesn't violate relativity. Nothing is moving through space faster than light. Space itself is expanding, stretching the distance between us and those far-off regions faster than photons can close the gap. It's a subtle but crucial distinction. The speed limit in relativity applies to objects moving through space, not to the expansion of space itself. So there's a hard boundary, the cosmic event horizon, beyond which information is permanently inaccessible. And here's what's really interesting. That boundary isn't just about distance. It's about information. It's an epistemic wall. Everything beyond it is, for us, as if it doesn't exist. Not because it doesn't. It almost certainly does. But because no signal, no influence, no evidence of any kind can ever cross from there to here. It's the ultimate edge, not of the universe, but of our universe, our knowable reality. Now, this idea has a deep connection to something from an entirely different branch of physics: black holes. And that connection is worth exploring because it illuminates just how fundamental these information boundaries really are. When Stephen Hawking and Jacob Bekenstein were working on black hole thermodynamics in the early 1970s, they discovered something astonishing. A black hole has an event horizon, a boundary beyond which nothing, not even light, can escape. And Bekenstein realized that this horizon isn't just a geometric feature. It has entropy. It stores information. In fact, the amount of information a black hole can contain is proportional not to its volume, which is what you'd naively expect, but to the surface area of its event horizon. This was shocking. It suggested that the maximum amount of information you can pack into a region of space is determined by the boundary of that region, not by the region itself. It's as if the universe is a hologram. All the information about the interior is somehow encoded on the surface. This idea eventually grew into what's called the holographic principle, championed by Gerard 't Hooft and later formalized by Leonard Susskind. Yes, the same Susskind from the string landscape we were just talking about. And here's the thing. The holographic principle doesn't just apply to black holes. It appears to be a deep feature of quantum gravity, whatever quantum gravity turns out to be. And some physicists have argued that our cosmic event horizon, the one created by the accelerating expansion, might work the same way. The information accessible to us, the total amount of stuff we can ever know about, might be bounded by the area of our cosmic horizon, not the volume of our observable universe, the area of its boundary. Think about what that means. It means there's a finite amount of information available to us. A huge amount. Don't get me wrong, we're talking about something like 10 to the 122nd power bits, which is an absurdly large number, but finite. And that finitude has consequences. It means that our ability to make ever more precise measurements of the universe has a ceiling. At some point, we run out of bits. We run out of distinguishable states. The universe, from our perspective, becomes grainy. Not because it is grainy in some absolute sense, but because our horizon limits how much information we can access, and information is the raw material of knowledge. This connects back to something we touched on earlier. That paper by Lawrence Krauss and Robert Scherer about the cosmic dark age. Remember, they pointed out that in the far future, the accelerating expansion will push all other galaxies beyond our horizon, leaving future astronomers in what looks like an island universe. They'll have no evidence of the Big Bang, no evidence of expansion, no cosmic microwave background to detect. They'll construct a cosmology that's completely wrong, not because they're bad scientists, but because the evidence will have been erased by the expansion of space itself. The universe will have hidden its own history. But here's the deeper version of that worry, and it applies not just to future astronomers, but potentially to us, right now. How do we know that the expansion hasn't already hidden something important? How do we know that some crucial piece of evidence, something that would completely change our understanding of cosmology, isn't sitting just beyond our horizon, forever out of reach? The honest answer is, we don't. We can't. That's the whole point. The horizon isn't just a practical barrier, it's a fundamental one. And it means that every cosmological model we build, lambda CDM, quintessence, cyclic models, eternal inflation, all of them, is necessarily based on incomplete information. We're constructing a picture of the whole from a part, and we can never be sure that the part is representative. This is where the cosmological principle comes back, and you can see why it matters so much, and why it's also so philosophically fraught. The cosmological principle, the assumption that the universe is roughly the same everywhere, is what allows us to extrapolate from our observable patch to the whole. Without it, we're stuck. We can only describe what we see, and we have no basis for saying anything about what lies beyond. But the cosmological principle is an assumption, a very reasonable one, supported by everything we observe within our horizon, but an assumption nonetheless. And it's untestable in the most fundamental sense. We can never check whether the universe beyond our horizon looks like the universe within it. We just have to trust that it does. Some physicists are comfortable with that. Others find it deeply troubling. And there's a philosophical position, sometimes called cosmic humility, sometimes called observational limits, that says we should be explicit about what we're doing. We should distinguish between what we've measured, what we've inferred, and what we've assumed. And we should be honest that some questions about the universe might be permanently unanswerable. Not unanswered. Unanswerable. Is the universe infinite? Maybe. The flatness measurements from the CMB are consistent with infinity, but they're also consistent with a very large, finite universe. We might never know which. Does the multiverse exist? Maybe. Eternal inflation predicts it, and eternal inflation follows naturally from our best models of the early universe. But we can never observe another pocket universe directly. Are the laws of physics the same everywhere? Maybe. We assume they are, and everything we've seen is consistent with that assumption. But everything we've seen is a tiny fraction of what might exist. And you know what? I think there's something genuinely peaceful about that. Not frustrating, peaceful, because it means the universe will always have mystery in it. Not the kind of mystery that comes from ignorance, which can be cured by better instruments and smarter theories, but the kind that comes from the structure of reality itself. The universe is built in a way that guarantees it will always be larger than what we can know about it. There will always be more, always another horizon. Think back to where we started, all those hours ago. Archytas of Tarentum, standing at what he imagined to be the edge of everything, reaching out his hand. What happens at the boundary? Is there something beyond? And every answer we've found, across 24 centuries of human thought, has been the same. Yes, there's always something beyond. The edge of the crystal spheres gave way to the depth of the Copernican cosmos. The edges of the Milky Way gave way to Hubble's galaxies. The edge of the observable universe gives way to the inflationary multiverse. And the edge of what we can know gives way to, well, that's the question we can't answer. And maybe that's okay, because here's the thing about edges. They're not really about endings. They're about the transition between what's known and what isn't. Every edge we've ever found in cosmology has turned out to be an invitation, not a wall. It says, there's more out there. You haven't figured it all out yet. Keep looking. And people are keeping looking. Right now, as you're lying here, the Euclid Space Telescope is mapping the geometry of the universe with unprecedented precision, trying to pin down whether dark energy is truly constant or evolving. The Dark Energy Spectroscopic Instrument is collecting millions more spectra, building on those tantalizing 2024 results that hinted at quintessence. The Vera Rubin Observatory is getting ready to survey the entire southern sky, cataloging billions of galaxies, looking for subtle patterns in their distribution that might tell us about the shape of spacetime on the largest scales. And theorists are working on the next generation of models, approaches to quantum gravity, refinements of inflation, alternatives to the multiverse, trying to find predictions that can be tested, trying to push the boundary of the knowable just a little bit further out. That's what's beautiful about this whole enterprise. It's not that we've figured out the edge of the universe. We haven't. It's that every generation pushes the boundary a little further, understands a little more, and in the process discovers new questions that are even deeper and stranger than the ones they started with. The universe rewards curiosity. It always has. From Archytas to Aristotle to Copernicus to Einstein to Lemaitre to Perlmutter to whoever's sitting in a lab right now, staring at data that doesn't quite fit the standard model, wondering if they're looking at a glitch or a revolution. And maybe that's the most comforting thought of all as you're drifting off. The universe is vast, possibly infinite, possibly one of countless pocket universes in an eternal multiverse, almost certainly larger than we can ever observe. And it doesn't have an edge, not in the way Archytas imagined, not in any simple way. It has horizons, surfaces beyond which we cannot see, boundaries that are real, but that say more about our position and our limitations than about the universe itself. The edge isn't out there. It's in here. It's the limit of what light has had time to bring us, the limit of what the expansion of space will ever allow us to receive, the limit of what information the cosmos is willing to share. But within those limits, and their generous limits, encompassing billions of galaxies and trillions of stars and a history stretching back 13.8 billion years, within those limits, the universe has turned out to be more beautiful, more strange, more elegant, and more surprising than anyone standing on that ancient Greek hillside could have possibly imagined. The cosmos isn't just big, it's subtle. It curves back on itself. It expands. It accelerates. It might inflate eternally, budding off new universes like some vast cosmic garden, and it hides just enough of itself to keep us wondering. So let that thought settle. Let it be the last thing on your mind as the night gets quiet. The universe has no edge, but it has horizons, and horizons are just invitations, dressed up as boundaries. There's always more beyond. There always has been. And somewhere out there, past the farthest galaxy you could ever see, past the cosmic microwave background, past the event horizon, past the limits of what any instrument could ever detect, somewhere out there, the universe is still going, still expanding, still being itself, whether anyone is watching or not. And that's enough. That's more than enough. Let it carry you the way it carries everything, gently, quietly, and without any edge at all.